Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Nasha binti Razali from Group 4. Together with my group members, Aina Nabilah, Rina Swari, and Wanu Suhaiza, we are going to present about gel dosimeter, or also known as chemical dosimetry. Gel dosimetry is also known as the first true three-dimensional dosimeter that important to determine dose distribution for complex radiation therapy techniques. This method was introduced by Gore et al. In 1984 to determine the spatial distribution of radiation dose in tissue equivalent phantom by using nuclear magnetic resonance imaging. Basically, there is three types of gel dosimetry, which are Freaky gel, alanine, and polyacrylamide gel. This system measures the absorbed dose by determining some quantitative changes in suitable material and any well-characterized chemical reaction. For instance, measuring the transformation of ferrum ion and also changes of viscosity. It is very helpful in evaluating and confirming complex dose distribution. Characteristic of gel system. It is based on radiation-induced and dose-dependent transformation of ferrous ion into ferric ions. These two ions, Fe2+ and Fe3+, are made up of different ionic radii and electromagnetic spin states. Water is the main material that being irradiated. Water interaction with ionizing radiations will produce ions, radicals, and molecules, such as H radicals, OH radicals, H2 molecules, H2O2 molecules, and H positive ions and OH negative ions. During earlier discovery of Freaky solutions were put together in gel matrices in order to provide spatial stability of dosimeters. Hence, nowadays it is known as gel dosimeters. Freaky solution is made up of ammonium sulfate, sodium chloride, and sulfuric acid. Sodium chloride is added to decrease any sensitivity of organic impurities. During conducting this experiment, it is important for all apparatus used to be taken care very carefully, because any contaminants exist can greatly affect the performance or the result obtained. Figure in the slides right now shows one of the example of Freaky gel dosimeter. This is one of the application applied by Babu et al. In a research conducted by them to reduce diffusion of ferric ions post irradiation and improving the spatial stability of those. The parameters that were observed during this experiment is concentration of ascorbic acid. All the gel samples were kept in refrigerator for 4 hours at 4 degrees Celsius. The next type of gel dosimeter is alanine. Alanine is one of the simplest form of alpha amino acid. It operates by measuring the difference between Fe2+ ions and Fe3+ ion present in the solution and the ion's radiation-induced concentration. This can be measured through spectrophotometric technique. This technique enables us to compare two wavelengths that correspond to ferrous ions and ferric ion. Wavelength of ferrous ion is 557 nanometers, while wavelength of ferric ion is 588 nanometers. DL-alanine enhance the ferric ions production when the solution of ferrous ion is irradiated. Irradiation of alanine creates radicals, which is proportional to the absorbed energy for wide energy range of doses. The presence of unpaired electrons is the concentration of radicals in alanine radicals. It's measured by electronic spin resonance spectroscopy. Usually, alanine dosimeters can appear in palette or film formats. Pal- Palette forms provide wider dose range due to its larger mass and more precise signal response. Dosimetric system of alanine gel solution. This compound was proposed by Mizuno in 2007 uh, and the sample used were maintained in 1 hour at room temperature before irradiation. Some of compound used are ferrous ammonium sulfate, xylonol, sulfuric acid, D-L-alanine, tridistilled water, and gelatin. As can be seen in the figures right now, these are the two types of alanine dosimeter form, which is in pellet and film form. They can be used for medical device sterilization, surface sterilization, cross-linkings, and also food irradiations.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ainabla binti Abdul Rahman. So I'll be continuing presenting the gel or chemical dosimetry, which is the polyacrylamide type, and I'll be continuing the presenting the working properties and the comparison between three type of gel chemical dosimetry. So firstly, we go to the description of polyacrylamide dosimeter. So polyacrylamide dosimeter is a simple chemical dosimeter which is being developed based on degradation of polyacrylamide by X and gamma gradation. And it's also unaffected by fast and thermal neutron, and the dosimetry itself has dose rate and energy independent. It also can be easily made and read in laboratory, and which consists of 1 milliliter of an extreme dilute, 0.078% polyacrylamide solution dissolved in distilled water and contained in polystyrene or glass vial. So the working principle or the basic operating principle for polyacrylamide dosimeter, with the changes in viscosity of the solution through the fractionation of the polymer molecule by ionized water product is directly related to the ionizing relation dose received. The viscosity changes is easily measured at a constant temperature of 25 degrees Celsius with a microviscometer. It takes 20 minutes to make an accurate measurement with 0.5 milliliter of solution per viscometer. Most of this time is required for the solution to reach a temperature of 25 degrees Celsius. However, fairly good accuracy has been obtained in less than 10 minutes by taking measurement at constant room temperature. So as we can see here, this is the photograph of polymer gel dosimeter with 2% weightage of HEMA and 0.2% weightage of 9G irradiated to a total dose of consist of from 0.5 to 20 kilogram. So the viscosity change varies to the dose absorbed by the gel dosimeter itself. Now we'll be discussing the dosimetric properties based on energy dependence on each chemical or gel dosimetry of freaky gel, alanine, and polyacrylamide. So the first one is freaky gel dosimeter, which is freaky gel dosimeter prepared using 5% by weight 217 bloom gelatin presents strong energy dependence for X-ray energy between 7.38 until 22.08 kilo electron volt, and it can be considered energy independent for effective energy higher than 30 kilo electron volt. This is based on Kelvinator and campus no date. So next one is alanine dosimeter from the batch rank Short, Rose and Hole 2003. It says that the alanine dosimeter have a weak energy dependence to high energy X-ray and high energy electron beams in the megavoltage range. So lastly is for the polyacrylamides. Polyacrylate by Bonney 1961 has a dose rate and energy independent. It is stable over long period of time before and after irradiation, and it is simple to make and read. So next property is sensitivity, which is the sensitivity of dosimeter of polyacrylamide, freaky dosimetry, and alanine dosimetry. So the first one from Nelson and Charles 1964, it said that polyacrylamide has sensitivity which there's approximately 3% decrease in viscosity for 100 radian of 1 gray of cobalt 60 radiation. While for sensitivity from freaky dosimetry, it demonstrated that freaky dosimetry system designed for low dose range certainly exhibit linear response capable of reliably measuring dose value within the range of 25 to 3000 mg. This is from Macaulay and Nasser Node. Sorry. So lastly is alanine, which have high sensitivity to radiation damage, and it is sensitive to low energy X-ray from Bertrand et al. 2003. So the last dosimetric properties we will be discussing today is dose range. So the first one from polyacrylamide started from Bonney 1961. It has a range of 50 to 7500 rad or 0.5 to 75 gray. Next is for freaky dosimeter. It is useful in the dose range of 5 to 400 gray and for dose rates of up to 10 power of 6 gray per second. Lastly, for alanine dosimeter, it has the high dose alanine EPR dosimetry is a very precise method in the dose range from 1 to 100 kg. This is stated from Bugay, Bashuk, Kolesnik, Mazin, and Gaponenko nodes. So that's all from me. We'll be continuing our presentation of, from our friend next.
A very good day to Dr. Nurul Zahira No Asman. My name is Lineswari Rajasegren. I'll be presenting about the dose determination and practical consideration using ZEL or chemical dosimetry. First, we are going to look at the dose determination for gel or chemical dosimetry. The direct measurement of dose or dose rate in water under specific reference conditions for the calibration of the clinically radiated beam is referred to as reference dosimetry. The reference dosimetry is where the dosimeters are calibrated to accurately measure the radiation dose while providing traceability to standards of the laboratory. Radiation dosimeter can be defined as the device that is capable of providing a reading that is the measure of the dose deposited in the sensitive volume by the ionizing radiation. In chemical dosimetry system, the absorbed energy of ionizing radiation produces a chemical change in the absorbing medium, which is the sensitive volume of the dosimeter. The amount of chemical change produced is used to determine the measurement of absorbed dose. The most widely applied chemical dose standard for calibration is the Frick dosimeter. The Frick dosimeter is a solution that is made up of the composition as listed in the slide. The dose determination by Frick dosimeter depends on the oxidation of ferrous ions into ferric ions in an irradiated ferrous sulfide solution. A strong absorption peak is observed at a wavelength of 304 nanometer by the ferric ions, while the ferrous ion does not display any absorption at the corresponding wavelength. The concentration of the ferrous ion produced in the solution can be identified using an absorption spectrophotometry. Spectrophotometer is an instrument that is made up of two instruments, which is a spectrometer and a photometer. A spectrophotometry is a standard and inexpensive technique used to measure light absorption or how much a chemical substance absorbs or transmits. The spectrophotometry is able to determine the concentration level of the ferrous ions by measuring the absorbance of the solution in the units of optical density (OD). The response of the Frick dosimeter is expressed in terms of the sensitivity of the dosimeter. The dosimeter sensitivity is also identified as the radiation chemical yield value, which is the G value. The radiation chemical value can be defined as the number of moles of ferric ions produced per joule of the energy absorbed in the solution. The average dose absorbed by the Frick dosimeter can be described by the change in optical density at the wavelength of 304 nanometer. The formula that can be used to calculate the Frick's dosimeter average absorbed dose is as following. To measure the absorption of the Frick dosimeter, we need to know the values of four factors, which are the molar extinction coefficient, yield of ferric ions, the density of Frick solution, and the path length over which the optical signal was read. Next, we are going to look at practical consideration using gel dosimetry. There are a number of practical considerations that can make gel dosimetry a good candidate for radiation dosimetry. First is the permanent data storage ability. This ability of the gel dosimetry makes the dosimetry a great choice for measuring radiation dose at remote locations. Secondly is the recording and displaying potential. The gel dosimeter's potential to record and display dose distribution throughout a three-dimensional volume makes the gel dosimetry more beneficial than conventional dosimeters, even in basic dosimetry application. Third will be the toxicity. Although gel dosimetry systems are fairly safe to be handled, certain components of gel dosimetry such as acrylamide requires extra safety precaution when handling it due to its toxicity. Next is the validation function of the dosimetry. Gel dosimetry has proven to be functional in validating simple multiple field arrangements and anatomical conditions with further complexity, which includes conformal therapy, tangential breast treatment, and scalp treatment using electron beam. Moving on to the next point, which is the oxygen contamination. The gel polymerization process in the dosimetry is commenced by free radicals. Even a small amount of molecular oxygen is able to destroy the free radicals and eventually put a complete stop to the polymerization process in the dosimeter. Therefore, the gel in the dosimetry must be protected from the probability of oxygen diffusion. Number 6 will be the gel matrix. The use of gelatin gel matrix produces greater vision of the polymerized region and imaging facilitation of the gel by optical means in the gel dosimetry than when agarose gel matrix is used. Next, we will look at the estimation of dose distribution by gel dosimetry. The efficiency of the dosimetry made it possible to use only a single gel dosimeter to determine the dose distribution throughout a patient volume in multiple planes, which eliminates the need for multiple point dosimeter. Point number 8 will be the photopolymerization effect. When light hits the gel dosimetry, a process known as photopolymerization may take place, which will cause the overall sensitivity of the dosimeter to deteriorate. This photopolymerization effect can be prevented once the monomer and cross-linker mixture are mixed together with the gelatin solution. The next point will be the gel pH. At all temperatures and concentrations, when the pH of the gel increases, the relaxation rate of the gelatin also increases, which will eventually help to improve the gel response. Next will be the temperature dependence. In imaging purposes, the gel dosimetry exhibits temperature dependence, where the sensitivity of the gel is said to increase when the temperature decreases. The decrease in temperature causes the change in proton correlation times and proton exchange rates in the gel to increase, which will consequently increase the dosimetry's sensitivity. Therefore, it is very crucial for the gel to achieve a state of equilibrium to a constant temperature before using the gel for imaging purposes. Point number 11 will be the gel fogging occurrence. The use of high-grade chemicals when manufacturing the gels are very crucial to prevent the occurrence of gel fogging, which can eventually affect the performance of the dosimetry. Lastly will be the concentration of monomer and cross-linker in the gel dosimetry. The increase in the amount of monomer component in the monomer and cross-linker mixture that are added to shield the gel dosimetry from light has a positive effect on the sensitivity of the dosimetry, which also helps to extend the dose saturation point of the gel dosimetry. Okay, that will be all from me. Thank you.
Assalamualaikum. My name is Wanu Suhaiza binti Sukri and I will continue to the reliability of gel dosimetry to the radiotherapy. A major challenge in radiotherapy treatment is to deliver precise dose of radiation to the tumor with minimum dose to the healthy normal tissue. In radiotherapy treatment, it requires accurate measurement of three-dimensional radiation dose distribution. So, gel dosimetry is used to measure 3D dose distribution for complete delivery verification and quality assurance. It is necessary to meet the growing challenges of advanced radiotherapy technique, and it is used to minimize dose to healthy tissues and enhance target dose delivery to the affected tissue. So as mentioned before, there are some type of gel dosimeter that we can use in radiotherapy treatment. First is prickly gel dosimeter. It is simple, reproducible, and can be modeled in different shapes. It is easy to prepare and are tissue equivalent, but the use is limited because of the dependence on oxygen concentration. And then polymer gel dosimeter. It is more stable and non-diffusion property, but the affected by but it is affected by oxygen contamination and concentration of cross-linker. So before we use polymer gel dosimeter, we need to remove free oxygen from the gel. There are several types of scan in nuclear medicine application. For example, heart scan are the most common. In this scan, kidney as a sensitive organ absorb higher amount of dose as well as uterus and ovaries. As stated earlier, polymer gel can be used in medical phantom as valuable tool for determining 3D dose distribution in a medium. Polymer gel dosimeter can replace medical phantom material as media with features similar to the soft tissue. This type of dosimeter can consider as a suitable option for studying dose distribution in sensitive organ during the radiation therapy and nuclear medicine. The dose received in sensitive organ has important role during the radiation therapy and nuclear medicine. Okay, next I will continue to the advantages and disadvantages of gel dosimetry. First, the advantages of gel dosimetry. Gel dosimetry can act both as a phantom and a detector. Gel dosimetry offers the promise of precise and appropriate 3D dose measurement over conventional dosimeters. It is tissue equivalent measurement of precise dose and high spatial resolution. For freaky gel dosimetry, it is easy to prepare, yield reproducible results, and are tissue equivalent over a wide range of photon energies. Then, disadvantages of gel dosimetry. Gel dosimeters are affected by factors such as light and oxygen contamination, temperature, concentration of cross-linkers, gel pH, and gel lucidity. For oxygen contamination, it will degrade the performance of gel by removing free radicals produced by irradiation. So, free oxygen must be removed from gel to solve the problem. For the temperature, change in temperature have an impact on the sensitivity of polymer gels. And lastly, for the pH, acidic pH is related to poor dose response reproducibility.
Alright, that's all from us. Thank you.